In this video, we are going to implement the FFT that was earlier designed in Vivado HLS on an FPGA evaluation board. I'll first briefly discuss the Axis Stream interface which we use to pump data into the FFT module and also to get data out of it. A data source module has been created in Verilog for providing data in terms of an Axis Stream interface to the FFT. Now this will not be explained, the working of this module will not be explained as part of this video. However, the source code is available and you are welcome to look at it and try and understand how the Axis Stream interface is implemented. It is a relatively simple module involving a fairly simple state machine. We will then create a block design where we put in the FFT, two data sources, one for the input data and one for the expected output, and finally implement this first in simulation and then on the FPGA board. And we will test this on hardware. So let's look briefly at what we mean by an Axis Stream. Axis Stream is a protocol that essentially is a simple kind of a bus. What we mean by that is it has a capability of transferring data from point A to point B. Now in our case, what we will usually have is there will be a source of data. This is some module either designed in Verilog or HLS or maybe directly using schematics. And similarly, there will be a target or a sink. What we want is to be able to transfer data directly between these two modules, for which we are going to use three signals. The first, of course, is the data itself that needs to be transferred. And this is in general n bits. In our case, it would be 32 bits because we have 16 bits for real data and 16 bits for imaginary data. Now, when we transfer data like this from the source to the target, we also need something over here to indicate when the data is ready or valid and the target should actually accept it. Because as you will notice, there is no address bus that we associate with this protocol, which means that there is no way of actually specifying which data is being presented at a given point in time, and there has to be some signal that indicates when the data is actually valid. So that's one of the other signals that we have over here. This also goes from the source to the target. However, we could also have another situation where the target is not ready to accept data for some reason. Maybe it's in the middle of some computation and it wants to finish that before it accepts the next bit of input data. So how can it convey this information back to the source? We add another signal, but now in the opposite direction, and we call this, appropriately enough, ready. So the target can indicate when it is ready to accept data, and the source can indicate when the data that it is putting out is valid. When both these conditions are satisfied, that is the source data is valid and the target is ready to accept data, one piece of information is transferred from the source to the target. In the next clock cycle, assuming that both valid and ready are still high, another piece of data will be transferred. So it's up to the source to make sure that on every clock cycle, it updates the data present on the data bus. If by any chance it does not have appropriate data, then it has to make the valid signal low. Similarly, if the target is not ready to accept data, it should make the ready signal low from its side. Now, in this protocol, one additional piece of terminology, the source over here is usually called the master, and this interface is called the Axis Stream master interface or Axis master. Similarly, the target over here is the slave, and this side of the interface is the Axis slave interface. Now, as you will notice, these interfaces are slightly asymmetric because the master is the one that gives out data as well as the valid signal, and the slave is the one that gives out a ready signal and accepts data and valid. Now, for our purposes, we have already generated the input data in a hex format using the DataGen script that was used when we set up the FFT HLS project. We would like to load this same data into some kind of Verilog module that can then act as an Axis master and give out this data. In the source code associated with this project, there is one such file. It's a Verilog module called datasource.v, it takes as parameter an input file name, which is basically the file where the hex data is stored. And if you look through it, you will realize that this is basically just a fairly straightforward implementation of a state machine. It's a very simple form of state machine. It has multiple states, mainly to account for the fact that the block RAM in which the data is stored has a certain read latency. But apart from that, all that it does is it basically starts putting out data, and from that point onwards, the valid signal is permanently high. It only then responds to the ready signal coming from the slave. By doing this simple module is able to send out data that can then be consumed by our FFT module, or as we will see in the final design, by the expected data output in the test bench as well. We are now ready to create the Vivado project for implementing the design on hardware. We will go into the same build directory where we first created the Vivado HLS project, which is the FFT32, and also the earlier project that contained the demonstration of the ILA and VIO. This same project directory also contains two .mem files. One is the input hex and the other is the output hex. These will be used in our present project for providing the input and the expected output. We can start up Vivado and create a project just like we did in the case of the ILA and VIO demonstration. We will use the same target hardware. We are going to begin by creating a block design. Now we want to add the FFT IP into this design. To do that, first we have to go to settings, click on the IP repository, and here use the plus sign in order to add an IP repository. What we can do over here is select the FFT32, the Vivado HLS folder that we used for creating our original design. And once we select that, it basically says add repository. One repository was added to the project, and it says it found one IP inside it. This was the IP that was generated earlier while running the Vivado HLS project. After we export it, it shows up in a format that Vivado can then recognize. Now, when I click on the button over here to add IP and then search for FFT, I can see that it shows up the FFT IP details over here. This is just the information and IP generated by Vivado HLS. These were all the information that I just left as defaults while exporting the IP. It of course puts in vendor as Xilinx because it was exported by Vivado HLS. You could have replaced it with whatever information you wanted. The important thing to keep in mind is to make sure that the repository path itself is correct. It is inside the build/FFT32 folder. So it is the IP that we actually created. You can see that it has a clock, reset, an AP control interface, which we will get to in a moment, and a data in and data out interface, both of which are AXI stream because that's how they were specified in the Vivado HLS design. Let's add a clock wizard to this so that we can actually get a signal in here. Go ahead and apply connection automation so that these signals get connected as outputs. But what I'm going to do is rename the signals. To reset and CLK. This is purely for convenience. It is absolutely not necessary to have these particular names. It's just that I have used these names in the test bench, so I'm going to stick with these values over here. The clock wizard itself, make sure it's configured correctly. It assumes that it has an input clock frequency of 100 MHz and also an output clock frequency of 100 MHz. Take the clock output, connect it to the AP_CLK pin of the FFT. Now the locked output basically will be low until the PLL has actually locked properly, which means that we can actually use it for our active low reset signal for the FFT. It will ensure that the FFT does not start operating until the PLL has actually locked. We also need to have something which will allow us to directly start the FFT as soon as the system comes on. what I'm going to do is just connect the start signal of the FFT to a constant. By default, this value has a constant value of 1, which means that I can now expand the AP control interface, take this output, the AP start, and connect it up to the constant D out. Let's just rearrange the design automatically so it looks a bit cleaner. Alright, now I have data in and data out to be taken care of. For doing this, what we are going to do is to use the data source module that I just showed you briefly earlier. The way to do that would be first go here to sources, click on design sources, right click and add source, add or create design sources, and we are going to add 3 files over here. These 2 files, the input hex.mem and output hex.mem, are to be added because they will then be used by the data sources. But in addition to this, I also want to add the data source.v from the Vivado folder of the repository of the source code. Okay. Now what I want to do is to actually add this data source module into the block design. So I can right click on it and say add module to block design. It creates something called data source underscore 0. I'm just going to repeat this process one more time. The reason for that will become clear later. I will basically be using it in order to also configure the output data. So I have 2 data sources, data source underscore 0 and data source underscore 1. Let's just double click on each of them. The first one has the default inp underscore hex.mem as its input file. I'm going to leave it at that because that's the correct value. Remember that I can leave it as just the file name because I have also added the file as part of the project itself. Now I go to data source underscore 1, double click on it, and now just change this name to out underscore hex.mem. Now what do I need to do with these signals? Let's first take the clock and connect it up properly. And similarly, the reset signals are connected up appropriately. Once again, let's just redraw the picture. It looks a bit cleaner this way. Okay, now what I need to do is to take this data source 0 output and I can directly connect that to the data in. But what I'm going to do is instead of that, I'll skip that step. And because I want to also add an ILA to monitor these signals. So I will first add an IP, the integrated logic analyzer, double click, change it to native type, and the number of slots in this case, I'm going to make it 8. What are the ports? The first one is going to be the data source and its corresponding valid signal. The next one is going to be the FFT output and its corresponding valid signal. And over here, I'm going to use the actual output of the data sync, the data source underscore 1, which is the expected output and its corresponding. Well, we don't really need to look at its valid signal because it's always going to be 1. The last 3 ports will be used to monitor the output signals of the FFT module itself. Okay, so now I have this over here. What I can do is just connect the clock. It automatically connects it up to the system clock, which is fine. And now what I would like to do is open up these signals and connect them appropriately. So what I've done is I've opened up the interface underscore access of data source underscore 0 and also the data underscore in of the FFT underscore 0. I'll take this T data and connect it to the T data here, T valid to the T valid here, and T ready to the T ready here. But in addition to that, I'm also going to take the same T data signal and connect it up to one of the logic analyzer probes. Similarly for the, well, I don't really need to worry about its T valid signal, but that's okay. I can just connect it up over there anyway. What about the output of the FFT? Data, which is connected up here. T valid is connected to probe 3, which is 1 bit. What about the data source underscore 1? Its T data can be connected to probe 4. The T valid I'm going to ignore. I'm not really going to bother about this. Now there are just a couple of more things that we need to pay attention to over here. One is, what should I do for the ready signal of the FFT0? Since this is just a test module, I want the FFT to always generate its output and send it out in sequence as soon as it is ready, because I want to monitor it on the ILA. The simplest way to do that is set the ready signal equal to 1, the same constant that I connected to the start signal of the FFT. The next question is, what about the data source underscore 1? That too needs a ready signal. What do I do with it? Well, whenever the FFT has generated valid data, I will use that signal to trigger the next output coming out of the data source underscore 1. I don't really have any better way of knowing when the data source underscore 1 should generate outputs. As you will see, now everything is pretty much taken care of. It's just that the T valid output of the data source underscore 1 has been left unconnected. In addition to that, there are 3 signals out here: the AP done, idle, and ready of the FFT block. I'm just connecting them up to the ILA. They are not particularly useful in this case, but just they can be monitored for completeness. Once again, regenerate the layout. Now you can see that it looks a bit complicated, but it's actually not really complicated. It just has a clock wizard to generate a clock, 2 data sources, data source underscore 0, which is feeding data into the FFT, and data source underscore 1, which is generating expected outputs, and the FFT module itself that we created using Vivado HLS. The start signal of the FFT module is permanently set to 1, so that it is always in operational mode. Similarly, the ready signal at its output is also permanently set to 1. Okay, now the next thing that we would like to do is to run a simulation of this entire system to make sure that things are working correctly. We can just add or create simulation sources. And the file that we are going to add over here is the FFT32 underscore tb.v from the same Vivado source code folder. There is one more step that we need to perform before we can run a simulation or implementation. Remember that we have to create an HDL wrapper for our design, and we can let Vivado manage the wrapper. Notice that as soon as we add the wrapper, the design underscore 1 underscore wrapper module becomes the top module. And in fact, the data source modules go somewhere deep into the design. You can't even see them at the top level anymore. That is perfectly fine. If we open the simulation modules, you will find that the FFT32 underscore tb.v contains the design 1 wrapper inside it. That's because it was written to instantiate the design 1 wrapper. You will also notice that I had used the signals CLK and reset over here as the signal names, which is why I had to rename these signals while creating the block design. And now I can run a behavioral simulation. Now once the simulation viewer opens up, you will notice that there is really no signal of interest out here because the test bench only contains clock and reset. So if you want to see anything interesting, you'll actually have to go inside the design 1. And over here, you can now start to look at some more interesting signals. In fact, the design 1 instance would be a good place to look for the signals that we are interested in. One of them would be the data source output data and its corresponding valid signal, the FFT data output and its corresponding valid signal, and similarly the data source 1 underscore data. And if we now run this simulation, we can just restart the simulation and run it for, let's say, 10 microseconds. What we will see is, you can see some activity out here. So for example, right at the beginning, you can see that there is one section out here where the data source is being made valid and is actually changing its value. When does it start changing its value? Actually, in order to see that, you need to add one more signal out here, which would be the FFT in ready. So we can just view that again, and what we will find is that right at the beginning you find that the FFT in ready corresponds to the values of the source data. So when the in ready and the t valid are both equal to 1, that's when the data from the input hex.mem actually starts getting fed into the FFT module. Now let's zoom out, and you will eventually see that it is after quite a while that the actual output starts to appear, right? So nearly 8 microseconds is the amount of time that it takes for the entire FFT to compute. If you recall the Vivado HLS synthesis report, there was a roughly 800 clock cycle latency, which at a 10 nanosecond clock corresponds to almost roughly 8 microseconds. So that makes sense. It's pretty much what you would expect. Now what happens here? Let's look at the output, right? The FFT output data is coming on this signal, and the expected output is coming on this signal. If we go look at this value out here, you will notice that when the t valid, the output of the FFT, becomes equal to 1, the corresponding value of the output data is some value 000f 00d9. Remember that the first 4 hexadecimal digits over here correspond to the imaginary part, and the last 4 correspond to the real part. Similarly, the output data also, the first 4 correspond to the imaginary part and the last 4 correspond to the real part. You'll notice that they don't actually match. But if you look closely at the numbers, 00D9 and 00EA are actually quite close to each other. Remember that the D9 and the EA are both referring to the portion that is in the fractional part, because this is 16-bit data with an 8-bit fractional part. What about the next output, F4CB? Well, the expected output was F4CE. 0328, the expected output was 0334. At the next value, FF75, it was expected to be FF7D. 0C84, it was expected to be 0C8A. You can go through like this and do the comparisons. The important thing to keep in mind is this was precisely the part that was automated in the C test bench, where what it did, rather than looking at the exact values that were being generated, was to compute the norm of the output, the difference between the expected output and the actual output, and check that it fell within an acceptable tolerance value. Okay, now that we are satisfied that the simulation seems to be working properly, we can actually end the simulation. Just close this window. Okay, to close the simulation. We are ready to go forward for the implementation, but before that we would also like to add a constraint file over here. Remember that we need to set the pin locations properly. So what I'm going to do is add a source file, add or create constraints, and I will add the pincon.xdc. If you look at this file, what you will see is that it basically sets the IO standard of LVCMOS 3.3 on the CLK port, and it also sets the package pin to W5. Similarly, the reset port also has the IO standard set to LVCMOS and the package pin set to U18, which is the central push button, as we discussed in the previous demonstration. Now with all of this in place, we are ready to generate the bit stream. We can of course go through it step by step, run synthesis, run implementation, and generate bit stream. I'm going to jump straight to the end. Alright, so once the bit stream generation has successfully completed, we can once again open the hardware manager, open the target auto connect, and right click on the Artix device, program device, make sure that the .bit and the .ltx probe files correspond to the project that you have just run, and program. And now we can, since the FPGA has been set up, the design has been set up in such a way that the FFT is scheduled to start, that is its start signal is permanently set to 1, it would automatically have started as soon as the system switched on and the clocks stabilized. So this is an example where you can actually see that the AP done signal occurs twice. In other words, at this point over here, at cycle number 179, and at this point over here in cycle 1012. The difference is somewhere around the 800 mark that was actually reported by Vivado HLS and seems to match exactly with what we expected. If you zoom in on this region, immediately after a done signal, you will find that this is where the next set of data for the next iteration of the FFT are being read in. These values that you see on the top row correspond to the values from the input hex.mem file. On the other hand, if we look at the part where the FFT out data is valid, we can go here and corresponding to that, take a look at the value generated in FFT out data and the data source _1_t data. You can see that exactly as we saw in the case of the simulation, the values match up quite well. So remember that you need to look at these values, or rather you should be looking at these values only at the places where the output t-valid is equal to 1. In other words, when t-valid is 0, the values could differ by quite a large amount, but that's not consequential because the value is not valid. But whenever t-valid is equal to 1, we find that the FFT out data and the data source _1t data match quite closely, well within the tolerance limits that we had set. So this concludes the demonstration of how to implement the entire FFT module on hardware. To recall, what we did was we created the FFT block first in Vivado HLS and then instantiated it into a Vivado block design. We also created a custom module called a data source that is capable of reading data from a file in hex format and then outputting it as an AXI stream. We used two of these data sources, one to feed the FFT module, the other to compare the generated output and see whether it was accurate. We used an ILA, an integrated logic analyzer, to monitor all the outputs and see that they were correct. That includes the done signal of the FFT module, and by looking at the waveforms that were generated, we found that the latency matched with what was expected and what was seen in the Vivado HLS output design.